Hi, my name is Kelsey, and together with Sarah, Belle, and Julia, we will present our project Understanding Global Air Quality and Mortality. Our presentation will cover introduction, the research questions, our data sources and preparation, key data tables, descriptive statistics, our graphs and visualizations, and our final conclusions. Introduction.
We are studying air pollution because it is the second leading global risk factor for death, impacting health and well-being worldwide. Understanding mortality rates from air pollution is key to guiding public health responses and identifying high-risk areas. Our analysis aims to examine deaths from air pollution and annual PM 2.5 exposure across countries from 1990 to 2020. By exploring regional and temporal changes, we aim to understand the relationship between these variables and evaluate progress in reducing public health risks. We also hope to identify regions where mortality has decreased despite stable or increasing PM 2.5 levels, offering insights into effective mitigation strategies. Our research is guided by our overarching question: what is the relationship between air pollution and public health around the world? To break this down, we have our specific questions. What regions have the highest death rates from air pollution? How have deaths from air pollution and PM 2.5 exposure changed from 1990 to 2020? And lastly, what is the association between PM 2.5 exposure rates and deaths from air pollution across regions? These questions will help us explore the global and regional impact of air pollution on public health measured by deaths and identify significant trends and correlations over the past 3 decades.
Data sources and preparation. Now we discuss our data and how we prepared it. The first data source was pulled from Our World in Data, demonstrating the number of deaths per year per 100,000 people for each country attributed to different types of air pollution. We are specifically looking at outdoor particulate matter deaths, since we will also be looking at PM 2.5 deaths. Our outdoor particulate matter deaths will be our dependent variable, and the time span the data was collected in is from 1990 to 2020. This is the raw data sourced from Our World in Data to Excel. It still has data columns that we're not looking at, so we cleaned it up in the next slide. This is the cleaned data table of particulate matter deaths by country in 1990 and 2020 sorted by region. The screenshot shows only Africa, but it continues listing Asia, Europe, North, and South America. We use this data for visuals we will explain further, and Belle cleaned it up in a second way she'll talk about now.
To make a line graph for a data visualization later on in the presentation, I process the data in Excel by mass copy and pasting each country with a row for each individual year from 1990 to 2020. I sorted these countries alphabetically by region. Each year has a corresponding data point of how many deaths occurred in that year per 100,000 people from outdoor air pollution, which I transported into a separate spreadsheet and then stacked all the data on top of each other, and then uploaded and cleaned the spreadsheet in Tableau to make a few data visualizations. Okay.
The second data source that we pulled from was Gapminder, which provides annual PM 2.5 exposure levels measured in micrograms per cubic meter for each country. This dataset covers the time span from 1990 to 2020, allowing us to analyze long-term trends in PM 2.5 exposure globally and regionally. In our project, PM 2.5 exposure is a key independent variable for our statistical analysis, as we aim to explore its relationship with air pollution mortality rates and examine how exposure levels have evolved over time and across different regions.
This is the whole data table we downloaded into Excel from Gapminder for PM 2.5 exposure rates. It is sorted alphabetically by country, and we manually added the region for each country in column B. The columns are sorted by year from 1990 to 2020 with the data points for each country's mean annual exposure corresponding to the year and country. To create both the summary and descriptive statistics, I sorted the countries by region and deleted all the years except for 1990 and 2020 to see the total amount of change over 30 years. I then added a column where I calculated the rate of change for each year. And from this, we can see that the majority of countries from 1990 to 2020 had decreases in exposure to particulate matter. And for the second line graph, I did the same process that I did for the line graph in source number 1. I copied and pasted each country with a row for each individual year from 1990 to 2020, and then transposed the data for the amount of annual PM 2.5 exposure per year, and then stacked it on top of each other.
Key data tables.
This is the global summary data for both the average outdoor particulate matter deaths per 100,000 people by region and the total mean annual exposure of PM2.5 in micrograms per cubic meter by region. In both of the summary data tables, we can easily see that there have generally been decreases in both exposure and death rates from the year 1990 to the year 2020 in both variables, excluding the death rate in Africa, which increased by 5.6%. It is also important to note that for the total mean annual exposure, the sample size for these regions had different counts, with Asia having the most countries included, while South America had the least.
Descriptive statistics. These are the descriptive statistics for deaths per 100,000 people due to world outdoor particulate matter in the year 1990 and the year 2020. From this data table, we see that there was a decrease in global deaths from PM2.5 pollution as the global average dropped by 27.8%. The range also decreased. This data reinforces the conclusions made from the descriptive statistics data table. The range and averages decreased significantly from 19 to 20.
After calculating the descriptive statistics for the death rate globally, we broke down the PM2.5 exposure by region in the year 1990 and 2020 to compare the central tendency of range of each region. On this slide, we can see the region of Africa and Asia. For Africa, the average slightly decreased from 1990 to 2020, but it is not a statistically significant decrease. For Asia, both the range and the average decreased, with the range decreasing more significantly from 1990 to 2020. In Europe, the average mean annual exposure greatly decreased from 1990 to 2020, and the range also decreased drastically. North America had a sample size of 29, and the mean average annual exposure slightly decreased. The maximum decreased dramatically, and so did the range. And lastly, South America had the smallest sample size. The average mean annual exposure to particulate matter greatly decreased. South America also had the most significant drop in the maximum average exposure, and this is also reflected in the range, which dropped from 69.5 to 17.2 micrograms per cubic meter of PM2.5.
Here are the box and whisker plots to show the change in both central tendency and dispersion from 1990 to 2020. The boxes on this graph represent the interquartile range of the data, which shows the middle 50% of the data points for each region. We can see that all regions around the world decreased in the average annual exposure to particulate matter except for Africa, which stayed about the same. South America had the greatest change. Africa and Asia showed the highest median PM2.5 exposure with broader variability and higher outliers compared to other regions. Asia has the highest single PM2.5 outlier, which is Qatar. South America also has two outliers with high exposure, which are Bolivia and Peru.
Data graphs and visualization.
Our first sub-question aims to answer the question, which regions have the highest deaths from air pollution in 1990 and 2020?
To answer this question, what regions have the highest deaths from air pollution in 1990 and 2020, we made chloropleth maps to convey the geographical distribution of impacts of air pollution in terms of the amount of death it causes. Using the outdoor particulate matter deaths per 100,000 for each country in 1990 and 2020, we can see which regions bear the greatest burdens of death and how this has changed over the last 30 years. By comparing these graphs, we can see that for both years, Africa, Asia, and Eastern Europe have the greatest deaths from air pollution globally. We can also see a general pattern of decreased deaths globally from 1990 to 2020 overall, but the relative amount of deaths are still higher in the regions of Africa and Asia. A few countries did see an increase in deaths: Egypt, India, and Mongolia. These visualizations help us understand where there is the most risk of air pollution-caused deaths, and this is significant to inform approaches to mitigating air pollution exposure and improving public health responses.
So for our analysis of the results between 1990 and 2020, the regions with the highest total number of deaths from air pollution were Africa and Asia. Based on the chloropleth maps that were shown earlier, in 1990, the countries with the most deaths were Russia, Egypt, and Saudi Arabia, while in 2020, they were China, Egypt, and Iraq. Asia has the highest average deaths caused by PM2.5 pollution from 1990 to 2020. And some implications based off of this data analysis are that the regions of Africa and Asia have the highest deaths from air pollution due to factors such as having high population densities in their third world countries. They both face challenges in healthcare access, especially in rural areas. And there are also geographical and climate factors that contribute to high air pollution in these regions, such as the Sahara Desert in Africa, which is a significant source of airborne dust, and lots of valleys and winter smog in Asia, which traps pollution close to the ground, which is the air that we breathe is more affected.
Our second question aims to answer how both deaths from air pollution have changed from 1990 to 2020 and how PM 2.5 exposure rates have changed from 1990 to 2020. In this line chart, we can see that there has been a sharp decline in deaths per 100,000 people from PM 2.5 air pollution in Europe and a steady decline in both South America and North America. Asia stayed mostly consistent for the majority of years and has had a sharp drop since 2016. Africa is the only region that has had an increase in deaths from air pollution from 1990 to 2020. This is a line chart that shows the detail of every country's death from outdoor particulate matter pollution. Although a major downfall of this graph is that it is very clustered, since it shows pretty much all of the countries around the globe, we can see that there are a few outliers, such as Egypt, Qatar, and Bahrain, that have significantly higher deaths than the rest of the world. But they have all been declining in at least the last decade.
So this bar graph shows the total annual PM 2.5 exposure from 1990 to 2020 by region. Based on the data, Africa and Asia have the highest total exposure, and the regions with the lowest total exposure are South America and North America. There's also a significant gap between the total exposure for Asia and that for Europe, which shows the disparities against the regions of Africa and Asia compared to the Americas and Europe. And for the second bar graph, it shows the average annual PM 2.5 exposure from 1990 to 2020 by region. And based on this data, we can see that Africa has the highest annual PM 2.5 exposure, and Asia has the second highest. The regions with the least annual exposure are North America and Europe. And a big difference between this bar chart and the last one is while South America has the lowest total PM 2.5 exposure, they have the third highest average annual PM 2.5 exposure.
Based on this line graph for median PM 2.5 exposure, we can see that Africa is higher than all other regions. Additionally, Asia, Europe, and South America are all decreasing their exposure, while North America and Africa appears to stay pretty much steady with slight variations. Between 2012 and 2016, many countries experienced a sharper decline in PM 2.5 exposure. This line graph shows every country, like the one for average deaths. And although the graph is admittedly more clustered, this graph shows some useful trends. For example, between 2012 and 2016, many countries experienced a sharp decline in PM 2.5 exposure.
We have the average outdoor particulate matter deaths compared to the mean annual exposure of PM 2.5 by region for 1990. We can see that in 1990, the regions with the highest mean annual exposure of PM 2.5 are Africa and Asia, and the one with the lowest is South America. Interestingly, we can see that despite having the lowest exposure, South America has the third highest number of deaths caused by air pollution. And another thing to note is Europe has the highest average deaths in 1990. And for this graph, it's basically the same one, but for the year 2020. And some noticeable differences are annual PM 2.5 exposure for all generations decreased, except in Africa, the decrease was so minimal, it's almost insignificant. The average deaths decreased as well for all regions, except in Africa, they actually increased slightly. And while Europe had the highest number of deaths per 100,000 people in 1990, they have the lowest number in 2020. And they experienced a highly substantial decrease in their PM 2.5 exposure. So for the analysis of the results from 1990 to 2020, the average deaths from air pollution have decreased in all regions except for Africa. Its mortality rates remain steady due to persistent challenges such as a reliance on biomass fuels, and limited policy enforcement. While global efforts have led to improvements in most regions, Africa remains disproportionately affected, underscoring the need for targeted investment and stronger regulations. PM 2.5 exposure rates saw significant declines in Asia, Europe, North America, and South America between 1990 and 2020, especially between the years of 2012 and 2016, which is most likely due to the Paris Agreement and WHO air quality guidelines being upped. And countries began aligning more closely with the World Health Organization during this time. However, Africa saw almost no decrease in their exposure rates, which highlights the disparities amongst effective healthcare in regions such as Asia and Africa.
To further understand the relationship between our variables, our next question is, what is the association between PM 2.5 exposure rates and deaths from air pollution by region? To answer this question, we need a scatter plot and trend lines with R values from regression analysis to help us understand the relationship between PM 2.5 exposures and deaths for each world region. I plotted each country by region with median PM 2.5 exposure as the x-axis and median death rate per 100,000 as the y-axis. The R values are shown on the right, and we see that Africa is at 0.07, Asia is at 0.41, Europe is 0.61, North America is 0.49, and South America is 0.25. And we can see that with these amounts of deaths and exposures and associations, the stronger correlation in Europe and North America suggests that increases in PM 2.5 exposure are more closely tied with air pollution mortality, and these regions could have more pronounced health impacts from their pollution levels. There are also weaker correlations in Africa, Asia, and South America suggest that there are factors other than PM 2.5 exposures that could be influencing these mortalities, like other sources of air pollution or healthcare infrastructure. Like mentioned in our previous analysis, we talked about Africa having a high PM 2.5 exposure and an increase in death over time. So understanding that there's a weak association with this specific air pollution variable helps lead researchers to further understand what more research could be done to understand the causes of these mortality rates.
To recap, our analysis revealed several key findings. Between 1990 and 2000, Africa and Asia had the highest total number of deaths from air pollution, highlighting regional disparities. Globally, both deaths from air pollution and PM 2.5 exposure rates decreased, suggesting progress, though the decline may vary by region or be influenced by other factors like healthcare or policy. We also found a positive correlation between PM 2.5 exposure and deaths from air pollution, but this was only observed in Europe. In other regions, the correlation may be weaker, suggesting that factors beyond PM 2.5 exposures suggests that other pollutants or healthcare disparities are influencing mortality rates. This underscores the need for further research in other regions to understand the factors affecting air pollution-related deaths, particularly where correlation is less clear. One challenge in our analysis is how we divide the data into regions. For example, Oceania is grouped with Asia, which could mask important differences within these regions and lead to misleading interpretations. Another limitation is that PM 2.5 is only one component of particulate matter. While it's still a major contributor, other pollutants like PM10 are not included, giving us only a partial view of the full impact. Finally, our study only identifies correlation between PM 2.5 air exposure and air pollution-related deaths, not causation. Other factors such as healthcare access or socioeconomic conditions can influence the results.
Our findings highlight several important implications. First, the regional differences in PM 2.5 exposure and deaths emphasize global disparities in pollution and health outcomes, pointing to the need for targeted efforts in different regions. Second, our analysis underscores the importance of investing in cleaner technologies and renewable energy to reduce particulate matter emissions, which can significantly improve air quality and public health. Finally, our findings can inform international policies aimed at reducing air pollution. By understanding the relationship between PM 2.5 exposure and mortality, it can provide a direction for further research to understand other variable causes of these mortalities in order to inform policymakers and create data-driven decisions to protect both public health and the environment. Thank you.